Hello, everybody. We're live for practice number 10. I see Mr. Dazzi is there. Do you have any questions? Okay, very good. So we'll wait for a few more people to join. Did you do any practice tests? Okay. My recommendation to you and everyone else, Mr. Dazzi, is do at least one practice test a week. Okay. It will really give you an idea of where you need to work on. Even if you're Division B, if you do a Division C test, it can still tell you what things you're going to need to practice on. And also, by doing a lot of different types of tests, once you've solved all the problems on that test correctly in your own handwriting, you put that in your binder. That way, if a event supervisor writes a test that's based on previous tests, which a lot of them do, you'll be able to look into your binder and find maybe not the exact same problem, but a problem that's very similar. Okay? That's really important. Remember, the first rule is to always simplify a design such that it's simpler for you to understand. And I think we showed that with drawing that. You redraw the problem in your own handwriting to make it easier for you to understand. Say, okay, who else is on? So we got Mr. Dazzi, who's here every week. Oh, Mr. D. Did you have any questions, Mr. D? And in answer to your question, Mr. Dazzi, we are just going to keep going until people don't have questions. Outstanding. Second place. Very good. Did they have ribbons or did they have medals? Even better. All right. Well, very good. And I hope you did well in your other events as well. Was there anything in particular on the test that gave you troubles? And again, that's what we do. When you do a test, every test you do is another circuit analysis with LEDs. Now, was this Division B or Division C? Okay. So they probably were just using the LEDs as lights. But always ask if you need to include the forward bias voltage and LED resistor, or if you can assume they are ideal diodes. Okay. What that means is, and so we're going to go to the whiteboard here real quick. Okay. If I have an LED problem, Got my load resistor right there, okay? So I got an LED right here, and I'll just draw the light coming out of it. Or sometimes they'll just write LED under here. Now, if this is our problem, there's a couple of different ways you can replace that. One is you replace it with a perfect or an ideal diode, which would be something like this, very simple. Or they might have it where they say, well, it's got a forward bias to it, okay? Such that if it is on, you replace it with a little battery, low resistor, in an ideal diode, that battery goes to 0, and that resistor goes to 0 if it's on. If it's not on, or if it's not ideal, then you put that in, and remember it's usually like 0.7 for silicon or something like that. And you put a resistor in here, and it's usually really small resistance, like 0.1 ohms or something like that, but you still put it in. So that's a real one. Now, if it's reverse bias, like let's say instead of it being that way, it's this way. You know, if it's reverse bias, what ends up happening is now it's replaced with an open because it's off. Okay? Now, you do have a small leakage current, and that resistance is usually on the order. So you replace it with a resistor and a reverse bias voltage, and that reverse bias voltage is usually really, really small. And the resistance that you would put in there for a realistic one is going to be on the order of giga ohms. It's going to be really, really high. Okay. So Mr. Day, did that help? So you always ask a question, do you want to use an ideal, which is either it's on and it's a wire, it's just like a closed switch, or it's off and it's just open. So in other words, it acts like a switch. Or do you want us to include the forward bias and reverse, and the forward bias voltage and resistance? Okay. In which case, then you put those in. And by the way, a lot of the problems that I'll do, I won't usually do those in Division B, because in Division B, we really only wanted to use LEDs for their lighting capabilities and to know that current only flowed one way, in the direction of the arrow. When we get into Division C, that's where I would really want them to know about forward bias voltages, forward bias resistance, etc. Okay, transformers. By the way, this is actually one of the areas that I would recommend sending a clarification question on the national website. So I'm just going to go to Google real quick, just to sort of show you how I find these things. Okay. Transformer problems and solutions. Okay. So you'll notice that there are some questions and answers here about how to do transformers. Okay. You got some sample transformer problems. Okay. And so here's a very common one where you have an input with a primary coil and an output with a secondary coil. They're connected by the iron core. Since the iron core has a great permeability, okay, pretty much all the magnetic flux is kept within this iron core, okay? And what you'll notice is the number of turns of 1 divided by the number of turns of 2 you will notice that that is equal to the ratio of voltages, okay? So you can change the number of turns to either increase the voltage or step up the voltage. That's what they call a step up voltage one, or you can increase the number of turns on the output to reduce the voltage. And the inverse happens with the current. So you'll notice N1 divided by N2 is equal to V1 divided by V2 equal to I2 divided by I1. Okay? So, generally speaking, okay, if you look at it, if we want to reduce the voltage, have a step down transformer here, okay, just like what we had here, okay, we'll notice that it had 8 windings on the primary and 5 on its secondary, and it reduced it. So if I want to reduce it, I'll have more windings on the primary than I will on the secondary. But something like this would be a good thing to put into your binder. And you notice I just did a simple Google question. Mr. D, did that help? And the reason why I suggest that you may want to actually reach out and do a clarification request is because you're really not supposed to have a lot of AC problems in Division B. Okay? So, Mr. Dazzy, we just went over LEDs and we just went over sample transformer problems. I just typed in transformer problems and solutions, selected the first EDU one that looked good, and I found this really cool page right here, which shows how the ratio of the primary coil windings to the secondary coil windings, N1 divided by N2, the voltages follow it. So whichever side's got more windings will have the higher voltage. Okay. Okay. And then the current ratio is the exact opposite. Whichever one's got the most windings actually has the least current. And that sort of makes sense because if I have more windings, each one of those windings adds in more magnetic flux, and the flux has got to be the same on both sides. Okay. So I need more current on the side with less windings to make up for having less windings. Outstanding, Mr. Dazzy. I'm very, very proud of you. Number one recommendation I have when doing an LED problem, raise your hand if it's not written in the instructions about whether it's an ideal diode or whether you need to include in the bias voltages and the resistances. Okay? Any other questions? Did everybody have a chance to look at practice 10 or practice 11? Which one? I think it's practice 10 is the one we're doing today. Okay. So the important thing I would say for practice 10, if you look at practice 10 here, is that remember about multiple sources. You can put multiple sources in series and they add or subtract. And you can put multiple currents in parallel, multiple current sources in parallel so they can add or subtract. Kirchhoff's voltage law is only going to be asked in Division C, but it's a good thing to know. And basically what it says is that if I make a loop around anywhere around a circuit, so here I can actually have 3 loops. I can have a loop around here, I can have a loop around here, and I can have a loop around the whole thing. The voltages will all add up to each other. So if this is VB and I make this 0 volts and that VB for node 1, then what happens is I know that the voltage at R1 is equal to VB, and I know the voltage at R2 is equal to VB as well. So the voltage is the same. In a series one, when I do the same circle, okay, this node here is still 0. This is still VB. But the voltage VB to 0 now is broken up amongst R1 and R2. So this is a voltage divider. And so I've got VB, I've got a different voltage here, and I've got 0. Now, if these two resistors are the same amount, I know by my current splitting or my voltage splitting rules that this would be 1/2 over VB. So you try to look for symmetry, okay? So a KVL here is just a really simple thing that the voltage here of this battery is equal to the voltage of R1 plus the voltage of R2 plus the voltage of R3. Okay, and here's some more cases where a KVL would be really useful because the voltage of the battery here is equal to, if I start here, starting at 6, and 6, 5, and 4 are all equivalent. So I really only have one node right here. If I make this 0, then this right here is V battery. This is V2, which is the same as V3. So I've actually only got 3 nodes, 1, 2, and this one down here. And so the voltage here is the same, so the voltage of R2 and R3 is going to be the same when I do the KVL, but it's going to be split with R1. KCL is just real simply put, the current flowing into any node is equal to the current flowing out of that same node, okay? And so something to think about is that the current coming out of this battery is now split among the two in parallel, and then they're recombined here. In a series circuit, the current is the same throughout. So it's very much the inverse of a KVL. Okay, so an example here is that I1 is broken down into IR1 and IR2. Now, if R1 and R2 are exactly the same, I know that they're split evenly, and then they're recombined, so I1 is equal to I2. Another common thing is they'll draw the node and they'll draw the current going in. So in this particular case, I1 plus I3 plus I2 equals I4. All the ins equal all the outs. And then I solve the problem using algebra. We also talked about Wheatstone bridges, where here we basically have a symmetrical bridge here, okay? And what they were doing is they were trying to solve for the resistance right here, and all they really had back in those days were galvanometers, which were fairly decent voltage supplies. And what they found out is that if the ratio of R1 to R2 was equal to the ratio of R3 to Rx, if that ratio was the same, okay, then what you could do real easy is that this voltage here would be 0. Okay? So what you get here is R2 divided by R1. So R2 divided by R1 is equal to Rx divided by R3. So you can solve for Rx. And usually what they do is that they know these 3 resistances really, really well. Okay? And they can change the resistance ever so slightly until it gets into balance. Okay? So here's an example, and there's a lot of examples, but remember that when it's balanced, the voltage from D to B is 0. So is the current. We talked about Thevenin equivalent circuits, which is I can take any complex circuit with 2 output nodes and replace it with a Thevenin equivalent voltage in series with a Thevenin equivalent resistance. Here is how you would solve for that. You'll notice that the way that we solve for that is going to be very, very similar to how you solve for Norton later. So if I take this entire system here, I can then solve for VThevenin and RThevenin pretty quickly, and then replace all of this with one current source and one resistor, or excuse me, one voltage source and one resistor. So Mr. Norton said, well, I can do the same thing with a current source and a resistance. And just like we would expect, the current source and the resistance are in parallel. You solve them, amazingly enough, almost exactly the same way, okay, as you solve for the Thevenin equivalent circuits. And one thing that's sort of neat when we get into this, okay, is that when we solve the same problem to get the Norton equivalent, we find out that the R Norton is equal to the R Thevenin. And that's true all the time. And here's some of the things. R Norton is always going to be equal to R Thevenin. V Thevenin is equal to I Norton times R Norton or R Thevenin. I Norton is equal to V Thevenin divided by R Thevenin. So the key is to just use whichever one makes the problem easier to solve. So if it makes it easier to solve it with a current source or a voltage source, that's what you use for. Okay? Just make sure you draw it correctly. So that was basically it. So there used to be 14 people on these, and now there's only 3. Well, I know. The reason why we're probably seeing a few less folks is honestly, a lot of people have already made it through all of the practices, and they might be focusing on other events. But feel free to have other people join. We'd love to have it. Are there any other questions? Just promise me, Mr. Dazzy, you're going to do at least one test this week. If you can do 2, do 2. And do it like you would do a real test so you can see if your binder's good enough. Practice with whoever you're going to be in competition with. Time yourself, okay? And then figure out where you need work. Are there any other questions? How about for you, Mr. D? Any questions? Oh, wait, I gotta wait. So the other thing I would recommend is to really get in, do all the levels in the homework generator. What is a common thing that they would do with breadboards? Well, a common thing they would do with breadboards is that they'll give you a breadboard like this. And a common thing I would do is I would go ahead and put LEDs and resistors in here. Okay, and I would hook it up to voltage supplies with some batteries. I would tape around the batteries, see if you can do a battery identification. I would not tell you what the values are of these resistors here to see if you can do resistor identification. I would also want you to make sure that you know how to look at where everything is positioned to see how they're connected. Okay, and then I would probably have 2 wires coming out of it where you could measure a voltage, or I'd call that nodes A and B. I'd have you draw what the circuit diagram would look like, okay, to make sure that you would know how to draw it properly, okay? I would also, if it was Division C, I might even put in integrated circuit boards for things like operational amplifiers and an OR gates and that type of thing. So a breadboard is really used to tie a lot of components together. I've also seen them use those snap kits that you can get, those electronic snap kits. I've also seen them where they just wire it straight up together and use alligator clips. Generally speaking, what I would also have you do is I might give you a breadboard that's got a switch in it, and it might even not be working, and I ask you to troubleshoot the problem. Like if I've got a string of Christmas lights, see if you can use your multimeter to figure out which one's burnt out, or use it to measure resistances to figure out which one's burnt out. Does that make sense? So in the next one we get into troubleshooting. Number one problem with almost every circuit is power. Is it turned on? Is the battery dead? All those types of things. Number two problem is everything in tight and connected properly. A lot of times things aren't in tight, things aren't connected properly. I've even had it where I've unscrewed a light bulb just a little bit, just enough for the light bulb to go out. All you have to do is screw the light bulb in. Okay, so you check everything to make sure nothing is loose, everything's hooked up right. Then the other key thing is, again, you go back to the power. If you're allowed to measure it using your voltmeter, you measure the voltages and you use your electrical engineering skill to figure out whether or not, if I'm measuring a voltage here, does it match what I should be getting in the voltage? And then if I measure all the various voltages, is it which resistors burn out, which components burn out? I do not know what Tasmodo the program is. I do not what a Sonoff or Shelly is. I would look them up. The main program that we used for circuit analysis back in the day was something called SPICE. They have many, many versions since then. It's been like 30 years. And so they've come up with a whole bunch of different versions of electrical engineering analysis tools. Oh, it turns off and on your lights from your Alexa. Okay, very simple. So what it probably has is it has some sort of electronic switch in it. Okay, such that Alexa sends it a command, which then closes the switch or opens the switch. It's like a relay. Yes, electronic relay. Most of these things are electronic. They used to be more magnetic. I might ask you to draw what a relay looks like using a magnetic contact or whatever. The clapper, where you clap on and clap off with a clapper, that's also the same type of technology an Alexa uses. And it's also the same type of thing that you'd see like with your Christmas lights. They'll put a daylight sensor in it, and then the daylight sensor then switches it on and off whether the daylight's on. How do we find the steady state voltage across the capacitor with a resistor in series with it? Okay, the steady state voltage across the capacitor, if it has a voltage on it, is going to be the full voltage if that capacitor, because the capacitor will be acting like an open at that time. So you measure the voltage between there, and it's just like if there's a break, there's an open there. Okay, just like if the capacitor is fully discharged and you're charging it up, when the capacitor first starts out, it's like a short, and then the resistance keeps going up, and then it becomes like an open. Okay, and no current's flowing through it, but you've got a voltage across it. Okay, then if it's got a resistor in series with it, when it's fully charged, if it's in series, since no current can go through the capacitor, usually there's no voltage across the resistor. Usually, look at your diagram. Okay, and most of those are going to be division C. Okay, because what they'll really be asking you in division B is when you have a charged capacitor in steady state, is it open or closed? It's open. There's a certain voltage to it. Since you know the voltage, if you know the capacitance, you can determine the charge, and if you know the charge, you can determine the capacitance. So you've had a 5-volt battery, a 1 ohm resistor, and a 1 farad capacitor in series. What would the steady state voltage be? The steady state voltage for the capacitor would be 5 volts. The steady state voltage for the resistor would be a big old 0 volts, okay? Because, again, the resistor needs current. V equals IR, and if there's no current, I is 0. Okay? And since I know it's 5 volts and a 1 farad capacitor, okay, I know that that's going to give me 1 coulomb of charge. Okay, so that's like a really big capacitor. Like a 1 farad capacitor looks like a Coke can. And that's why you always guess. Okay. All right. So for homework, I want everybody to do yet another test. And I want you to do level 10 And if you're up for it, do a level 11 Wheatstone, but you should be able to do everything up through level 10 already. Okay. Hi, Mr. Sir Flim Flam. Yep, I think it's time to do a history check. Here's what I would like for you guys to do now, since y'all are actually better than me at this. Mr. D, can you send out a question for everybody to look up on their binder? All right, Mr. Dazzy, you're free on this, but keep in mind, you always need to have your binder whenever you're practicing, whenever you're doing your tests, etc. So, Mr. D, well, since it's just you and Mr. Flim Flam, then I'm going to give you the question that I have is, when did Volta invent his volcanic piles? Go. I'm going to see if I can look it up on the internet while y'all guys are looking it up on your binder. I got 1800. Yep. All right. So that would be a very good one to ask. Hold on a second. All right. Then my next question. Okay. Hold on a second. Of the scientists that were mentioned in the history section, who's the only scientist who was dramatically impacted by the French Revolution? Close. French Revolution, Ampere. Okay. Now, you got to remember, Ampere is the guy who determined that if you flowed current, like when he moved current back and forth, it disrupted the magnetic field and made his compass jerk around. Okay. So he's the one who determined that current can induce a magnetic field. Okay. Please find in your binder and put the formula out here. If I know the charge, what is the voltage and the capacitance? If I know the charge, what is the voltage and capacitance? If I know the charge, what is the voltage and capacitance? Okay. Mr. D, you are wrong. You were right. You did confuse it. If you know the charge, what is the voltage and capacitance? So Q is equal to CV. Okay? Not V divided by C. C is equal to Q divided by V. Okay? If I know the current and the resistance, what's the formula for the power? That is correct. I squared R. Okay. 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 Da, da, da. Which is more magnetic, platinum or copper? They're both very good conductors, but which one's more magnetic? Platinum or copper? You should be running to wherever you have permeability ratings for various materials. Which is more magnetic, platinum of a material, platinum or copper? One of them is paramagnetic, which means it's barely magnetic. And one of them is diamagnetic, which means barely negative magnetic. Okay, so if I look over here, the way I'm able to solve this real fast, okay, is you'll notice that platinum has a relative permeability of 1.000265. Copper, on the other hand, has a relative permeability of 0.999999994. So copper actually is diamagnetic, okay? So in other words, it actually repulses slightly, okay? Whereas platinum, on the other hand, is slightly magnetic, okay? You'll find that stuff is either magnetic, which means that you're talking your nickels, your irons, all your stuff that really gives good magnetism, like steel, okay, because it's got a lot of iron content, or it's not really very good at being a magnet at all. And it will be either slightly magnetic or slightly negative magnetic. Now that is correct, Mr. Martinez. Copper is an outstanding conductor. Outstanding. And not only that, it's very inexpensive, so it makes a very good conductor. That's why you see it so often. But we're talking about the magnetic capabilities. Okay? My next question is, if I have a copper wire that is 1 millimeter in diameter and I have a copper wire that is 2 millimeters in diameter, okay, which one has the least resistance? If I have a copper wire, same length, same everything else, that has a 1 millimeter diameter and one that has a 2 millimeter diameter, which one has the least resistance? Least resistance, Mr. D. So the least resistance is going to be the one with a bigger area. That's going to be 2 millimeters. Now, for the same length and the same all other parameters, if I got a 1 millimeter conductor and a 2 millimeter conductor, okay, what's the difference in resistance? So this one, the bigger one, is going to have less resistance than the smaller one, right? So how much difference is it? The 1 millimeter is actually going to carry less current because it's going to have higher resistance. So 1 millimeter is going to have a higher resistance than 2 millimeters. Think about it like a pipe. If you got a 1-inch pipe and a 2-inch pipe, which one's going to have more resistance? Well, the 1-inch pipe is going to have more resistance. The 2-inch pipe is going to have less resistance. Now, the other thing is that if you remember the equation where R is equal to rho times the length divided by the area, right? Well, our area is equal to pi r squared. So if I double the radius, I'm going to 1/4 the resistance. So my 1 millimeter wire compared to my 2 millimeter wire, the 2 millimeter wire has got 1/4 the resistance of the 1 millimeter wire. For the same length and the same material and the same surface area, okay, name me one other thing that I can use to increase or decrease the resistance of a conducting wire. So the area is the same, the material type's the same. The material is the same, okay, and the length is the same. No, you're doing right, because it varies as a function of length. It varies as a function of area, which means pi r squared, okay? And it functions as a type of material. But there's one other thing. Temperature. That's what I'm looking for. The hotter the material is, the higher the resistance, okay? So if I take a copper wire and it's in Alaska and it's really, really cold and I'm putting electricity through it, it goes a lot better than if I've got that same wire, everything the same, in the Sahara Desert where it's super hot, okay? And so that's why you'll notice, like a lot of things you'll see, we spend a lot of time trying to cool down conductors. It's to extend the life of the conductors, but it's also to reduce the resistance. The reason why temperature was not included in the formula is that the temperature formula is a little bit more complex. There is a temperature formula, okay, but it's a little bit more complex. I was really trying to just get the basics. Okay, so that's your binder check. Are there any other questions? So congratulations again on the good, strong second place finish. Just keep trying, and do as many sample tests as you can. Don't forget to keep doing the homework generator. All right, the next practice is going to be practice 11. Okay, that one's really important for Division B and Division C, as is practice 12. After we do practice 12, when we get into practice 13, 14, and 15, those are really only focused on Division C. However, any of you Division B people who want to call in and ask questions, feel free to continue to do so. All right, last call for questions. Okay, everybody, I will see you next week.